All right, welcome back to part 4 of the midterm review. So, in the last section, we talked about the photoelectric effect, and now we're going to move on to Hall voltage. This concept seems to confuse a lot of students, I guess, because there's multiple parts to it. So, we'll break it down one by one and we'll go from there. So, the first question here is we need to show the setup. So again, we have you need to be able to look at this and realize that which side is positive, which side is negative. So I'll give you a second to pause the video and figure that out. Okay, so the positive end here is the left side and the negative end on the right side. So the current, conventional current, I, is going to be traveling like that and then going through like this, like that. So if we say, for example, that we have now a magnetic field going into the page, like that, and sometimes I still have students confused about whether or not this is into the page or out of the page. The best way to think about it, and actually where the notation originally came from what I've heard, is that you can think of it as an arrow that you're either looking at or looking at it going away from you. And so if you think about an arrow, imagine my drawing is not very good, but if you think about an arrow, it has a pointy side, which is this, and it has the feathers, which is that. So as the arrow, sorry, is coming towards your eyes, it's going to be pointing, it's going to be a little dot like that coming towards you. So you should be able to very easily recognize which of these is which. Okay. So we have here B is coming out of the page. So I know a lot of students here know what to do as the next step. So what we need to do is figure out, is this an N type or P type semiconductor or metal? And in this case, I haven't actually gotten into the N type or P type topic yet, but regardless, this is not a theory review, right? As I mentioned, this is a application and kind of problem solving review. So when you have this situation, and oftentimes in questions, you'll get ones that don't show any of the circuit like that. You'll just get the current direction shown and the B, and then you might get a voltmeter hookup as well. So let's say we have a voltmeter like that. We'll put the positive end and the negative end. Voltmeter, oops, sorry. Like that. And the reading, let's say, is, I don't know, positive 10 millivolts. You should, with this setup here, you should be able to figure out if it's N type or P type. So I'm going to give you a second to pause the video again and work it out and figure out for yourself if it's N type or P type. If you have no familiarity with how you should do that, I'm going to walk you through it step by step, okay? But just be prepared that in the exam, you might get a question like this that just has a picture like this and asks you, is it N type or P type? This is sufficient information. So what we need to do, and I know a lot of students know that the first step is to use the right hand rule. However, this is what I found was interesting, was a lot of students know they need to use the right hand rule, but they don't know what actually they need to right hand rule. So remember that when we do right hand rule, we're doing a representation of a mathematical or physics concept, right? The mathematical concept that we're doing quote unquote right hand rule for is the cross product, don't forget, of something, right? So in this case, what are we doing the cross product of? We know that we have moving charges within a magnetic field. So what we're going to experience is F mag is Q, and this again comes from the formula sheet, VB, V crossed by B. And so this is the thing that's getting right hand ruled, and the cross product part of it, right? The cross products part, it comes from V crossed by B. So in order to do that, we need to do a few things. First of all, we can figure out what is F mag by doing right hand rule. And to do that, I'm going to label them very directly. We have index finger, we have middle finger, and we have our thumb. So again, I want you to pause the video. Which of the variables should we assign to each of the respective fingers? Okay, so take a second to pause the video, and I'll carry on in 1 second. Okay, so the index finger is the velocity, or the thing that's moving. In this case, the charged particle, because it's later going to be QV. But the thing that's the velocity, so we're going to call this one the current direction. The middle finger is going to be the magnetic field, B. And then our answer is going to be our thumb. Okay, so let's take a second to point our fingers in these respective directions. So our index finger is going to be pointing to the right. Our middle finger is going to be pointing out towards us. Okay, I'm doing it right now as I'm speaking to you. So which way would our F mag point? As a result of this, F mag points down. Okay. And now, so that's the first step. The second step is interpret the voltmeter. Okay. Interpret the voltmeter. I noticed when I was grading these in the tutorials, I noticed a lot of students would say something like it's p-type because the voltmeter reads positive. Well, the voltmeter only reads positive because we put the positive end there and the negative end there. If the negative was here and positive was here, the reading would be negative, okay? So that's not a sufficient enough explanation. So, the next step is we need to figure out, interpret the voltmeter. So as we know, if there's a positive reading, then everything is in the correct conventional way. So this side here will be positives, and the bottom will be negatives. Okay, so interpret the voltmeter. Where are charges building up? So in this situation, we have our positive charges at the top, negative charges at the bottom, and 3. Okay, so step 3, F mag will point to the direction of the main charge carriers. So in this case, F mag is pointing down, which is towards the negative charges. So for N-type or P-type, and the answer here is that it's an N-type. Okay. So it's really, really important that you be able to look out for all the different things that can change. First of all, the current can point right or it can point left. The magnetic field can point into the page or it can point out of the page. The voltmeter hookup can be positive at the top, negative at the bottom, or it can be negative positive. And the reading here can be positive or negative. So all of these things are possibilities. Okay. And remember that the current can be from the movement of the electrons or the holes. So I'm going to do a couple of examples if we have space here. Let's do a couple more examples really quickly. Actually, while we're here, okay, another common mistake that I've noticed is you see here, I'm going to zoom into the picture. Zoom into the picture a little bit. Okay, so you see, if we were to label the dimensions on this picture, we could say this is, let's go with green. We can say this is height. Okay, we can say that's height. We can say that's length. Or we can say this is width. And we can call this one length. Or actually, let's switch it up. Sorry. We'll call this one length. And we'll call this one width. So the important thing here is we have an equation from the formula sheet that is R, resistance, is equal to rho L over A, or L sigma over A. First of all, a common thing I saw was a lot of students made the mistake of thinking that this is density when it's not. Very, very important. And this is resistivity, it's called. And then you'll get this L over A. So keep in mind that in the questions, they'll often tell you current goes in the direction of L, or current goes in the direction of H, or current goes in the direction of W. In this case, current goes in the direction of L. So the L value up here is the direction that the current goes in. A then becomes the other two dimensions that are not L. Okay, so be careful for that, because I saw some students that would put L here, but then down here they're also using L again, let's say L times H or L times W, and making a mistake. So be careful for that, okay? Quickly identify what's L, and the other two become A. And while we're here right now, I'll tell you another common mistake. L, you'll get L will be reported in micrometers often, or maybe even meters. But conductivity here, and which we're going to get to in the next phase, is often a centimeters, I think, squared over centimeters squared v seconds, I think. I think that's the unit, but regardless, it's usually going to have centimeters, and I'll tell you why that is. And I'll see students plug in, let's say this was, I don't know, let's say it was 5 micrometers. They'll plug in 5 times 10 to the negative 6 at the top, and then let's say our sigma was like 0.22 cm or something like that, then this is meters, that's cm, this does not work. So what you need to do is make sure that you have consistent units, and I'll show you an example of that uh, coming up shortly. So actually, let's jump right into that. So we have, this is another thing that I'm sure will be tested a lot on the exam, conductivity. Okay, conductivity, resistance, and so on. So the equation in the formula sheet that you're given is sigma equals 1 over rho. Again, that's not density, okay? And that's E NO mu N plus PO mu P. So this is the electron concentration and the hole concentration. And these are constants for mobility, it's called. So you have electron mobility and your hole mobility, and these are from the formula sheet. They're material properties, okay? So here, the thing to look out for is you have three main scenarios. Three scenarios. So I don't know why when I use color it looks so bad like that, but anyways, so we have three scenarios. In these type of questions, they'll tell you intrinsic. They'll tell you an intrinsic germanium or intrinsic silicone or whatever, or pure, or not doped. So when they say this, okay, what they're saying is that NO is equal to PO. Now, concentration of holes is equal to concentration of electrons. And as a result of this, we have the equation Ni squared is equal to NO PO. But if NO and PO are the same thing, then they just are the same as Ni. So therefore, in this situation, Ni equals NO equals PO. And as a result of that, sigma ends up becoming E intrinsic concentration mu N plus mu P, where the this value, intrinsic concentration, again comes from the formula sheet, okay? So this is the first situation. I'm going to highlight this. So again, in a question, if they tell you you have intrinsic silicone, they're not going to tell you that this is the equation that you need to change. So this was the original equation, right? I'm giving you three scenarios where the initial is this. This is what's in the formula sheet that needs to be converted. So that's the first one. The second one, strongly p-type. So if we have strongly p-type, that means our concentration of holes is much greater than the concentration of electrons. And then sigma here becomes E, remember it was ENO mu N, right? Plus PO mu P. But now, because of this relationship here, this NO essentially becomes negligible. So sigma here will be equal to E PO mu P. So this is the second variation of the equation. And I'm sure you can guess that the third one, I'll do it here, 3, is strongly N-type, and everything is the opposite of P-type. So sigma is equal to E NO mu N. And so for these type of questions, you might get a question that says the concentration of holes within a strongly p-type is this. What is the resistance if the current is in this direction or whatever? Okay. But anyways, the point is that these sigma values, you often have to use them, and you have to be able to recognize what changes you may or may not have to make to that sigma. They only give you one of them on the formula sheet. And then the other thing is, okay, that the values, the other thing is that the intrinsic concentration or those carrier mobilities, mu p, these are all, so this one is cm per centimeters cubed, and these two are centimeters squared volts and seconds. So whenever, and that, but however, the spatial dimensions, however, L and A are usually in micrometers. Okay, so I can't tell you how many times I had students where they had to calculate R equals L sigma A, and they plug in the values, the value that comes before the times 10 to the negative 6 or times 10 to the negative whatever. They plug those in correctly so that they get like the first part of their answer, like let's say you get 5.01 times 10 to the negative 3 is their answer. That the 5.1 part is correct, but this part is incorrect because of the scale issue that they've had. Okay, so just to clarify, um, if L is equal to 32 micrometers, that means it's equal to 32 times 10 to the negative 6 meters. And if we want to convert meters to centimeters, we multiply by times 10 to the 2, so this becomes 32 times 10 to the negative 4 centimeters. Okay, so be careful. This is a very, very, very common way that I saw students getting incorrect marks here, is because they forgot to convert from meters to centimeters correctly. Okay. So I think that's everything. In the next video, we're going to talk about we're going to talk about energy bands. And yeah, thanks for watching, and I'll see you in the next one. Okay.